So in our previous lecture, we studied about gate trains, and then further we obtained the transfer function of electrical systems. And before that, we tried to find the transfer function of some mechanical systems. So we came across systems like translatory motions, the rotational motion, and the combination of them. So today we'll discuss about a system that is combination of electrical and mechanical systems. It's a sort of electromechanical system, so which is termed as servo motors. So we first define the term servo mechanism. So servo mechanism is a negative feedback control system in which the controlled variable or the output is mechanical position or its time derivative. Time derivative means the velocity or acceleration. So it's a sort of negative feedback control system in which we'll be having output in the form of mechanical position, velocity, or acceleration. And the term servo stands for slave or servant, while mechanism it's derived from the Greek word. So the servo stands for slave, while mechanism stands for machine. So they are classified into two types. One is the DC servo motor, the other classification is AC servo motors. So today we'll try to discuss a part of DC servo motor. So servo motors basically look something like this. So it's combination of certain components. So you have a plant or the process, the DC motor, so which is attached to a gear train. So we already have discussed about the transfer function. We obtained the transfer function of gear trains, and today we'll try to model the DC motor. So modeling of gear train has already been done. We'll model DC motor today. So this special motor accompanies few characteristics, like it will be having high speed and will be operating at low torque. So in order to switch or in order to change torque and speed, we'll be using gear trains. So it's combination of the motor, the gear trains, then the output is employed or is taken from this jaw, and the displacement or the velocity or the acceleration is sensed through a potentiometer or any other sort of sensors. So nowadays we have other sensors as well. This sensor feeds the information about the position or the velocity or acceleration back to a device which is control circuit. So now what you're doing is you're trying to compare the actual displacement or velocity or acceleration with what had been fed as reference to the control circuit. So if it matches, then in that case the voltage output fed to the motor will be 0. Let's say that you fed input to control circuit, or you gave a reference as 30 degree to the control circuit, and the DC motor operated and brought the load to 30 degree. So once the load had been brought to the reference angle or reference input, in that case the potentiometer will feed the signal, corresponding signal to 30 degree to the control circuit, and will be compared with the reference input. If in case the actual output will match with the reference input in the control circuit, in that case the voltage output to the DC motor will turn 0, and thus no further operation will be done. If you give reference input, let's say 60 degree, in that case again the voltage will be given to DC motor and will operate gear trains to further move the load to 60 degree. So this is how this works in a negative feedback fashion, and it continuously. Similarly, if you want, you can give reference input in the form of velocity or acceleration. So this system tries to match the load with the reference displacement or velocity or acceleration. So we try to model the DC motors today, specifically the armature controlled DC motor. So since you studied about DC motors in your previous year in electrical technology, you classified DC motors into many types, one of which was separately excited and self-excited. Moreover, you have motors which are permanent magnet in nature. So motors will be accompanying a field which will be either supplied through a permanent magnet, or it would be a wound field type motor. So this is something that you already have been studying, and you know all of. I assume that you know about this because this was something that had been taught to you in your previous lecture, previous year. So I taught you these things I provided you notes. So I guess that there must not be any problem with the classification of types of DC motors. So in this particular case, we are going to use a wound field separately excited DC motor. And since we are talking about armature controlled DC motor, which means that we'll be trying to control the load angular displacement, velocity or acceleration by controlling the input fed to the armature while keeping the field side input constant. So this means that now we have a variable input at armature side as Vi. This is why we have written here small vi. So this means that we are going to change this voltage in order to attain the output theta, which is whatever it is desired. So by changing the value of Vi, we'll be attaining the desired input, output theta. While during this operation, we'll be keeping the voltage Vf of the field as constant, and hence If will be constant, and thus the field that is being generated at the field side will be constant. So flux will be constant. Now here you have Ra is the armature resistance of the circuit, La is the armature inductance, Vi is the input armature voltage, Ia is the armature current, Eb is the back EMF, Tm is the torque developed in motor, J is the moment of inertia acting on motor shaft because of load. Then you have D as viscous friction acting on motor shaft, that will be again because of friction or air drag or whatever. So that will all be accompanied by the term D. Now the torque developed by motor Tm is given by the term Kf, Ka, If, Ia. So this was derived from the term that you already have studied previously, where motor torque is equal to Ka phi Ia. And if you remember, so I have got notes from one of your students of your class. So here are the notes. If you can see that this was taught to you that for a separately excited motor. So this is DC shunt separately excited motor. The torque armature current, when we try to obtain the characteristic for torque armature current, we came with the expression T equal to K phi Ia. So this is what is written over here. So you have Tm equal to Ka phi Ia, and since phi here is constant, which is proportional to If, If is constant, and flux is being produced by the current that is being fed to the field winding. Or this can be written as phi Kf If, where Kf is the proportionality constant, and thus the torque can be written as, if you substitute phi as Kf If into Ka phi Ia, then what you get is Tm is equal to Ka Kf If into Ia. So this becomes Ka Ia Kf If. So this is what is written over here, and here Kf Ka If are constants, and thus we take this term as Kt, which is Kt is nothing but the motor torque constant. It's called as motor torque constant, and thus Tm can be written as Kt times Ia. So let's call this equation as 1. Now if you talk about the back EMF that is being produced inside the motor, and which was proportional to angular velocity. So back EMF is proportional to angular velocity, and hence Eb can be written as, so this was, if you remember, Eb was given by an expression Np phi z over 60A. If you again see the notes, you'll find that Eb was proved to be equal to Np phi z over 60A. So here it is written. So you have back EMF which was equal to Z by A, and this is Np phi Z over 60A. So this is something that you have already been taught in previous year, and thus we are not going into much detail of how we obtain this expression. If you want, you can refer to the notes, and it is still there in your Google Classroom of your previous year. So if you are able to access that classroom, you can refer to the notes how to obtain Tm, which was equal to Ka phi Ia, and Eb, which is equal to Np phi Z over 60A. So now if you look at this expression, this can be further reduced to the form omega Kb. So omega, since n is the speed in revolutions per minute, which can be reduced to omega, and the remaining constant terms will be written as Kb, and thus Eb will be equal to omega times Kb, and this can further be written as Kb d by dt of theta. So omega is now substituted with the term d by dt of theta. Now, if you apply the KVL at the armature side of this motor schematics, so if you look at the armature side only, so you have a supply voltage or input VI, then you have a voltage drop IARA, then here you have a voltage drop LA DIA by dt, then again a voltage drop EB. So VI can be written as IARA plus LA DI by dt plus EB. So let's call this equation as 3. So we obtain this by applying KVL at the armature side of the schematics. Now if you look at the load side, so if you look at this load, which has moment of inertia as J, and the viscous force or viscous torque that is being operated or exerted on the motor shaft is D, and now we draw the FBD of this load. So J is the moment of inertia. The torque that is being applied to this is given by Tm. So this is the motor torque exerted on the load. Then again, now we have some resisting torques because of the moment of inertia and the viscous damping. So because of viscous damping, you have d by dt, d into d by dt of theta, and because of inertia, it's J alpha. So d omega and J alpha are the resisting torques acting on the motor shaft. Now we equate this to obtain the final equation Tm, which is equal to J alpha plus d omega, and let's call this equation as 4. Now from equation 1 and 4, so since from equation 1 we said that Tm, which was equal to KTIA, we substituted this value KTIA into this equation to obtain KTIA equal to J alpha plus d omega. Taking Laplace transform of this term, this equation, we get KTIA function of S. So since IA was a variable, the function of t, theta is function of t. Now we obtain variables with function of S. So KTIA S is equal to S square from double derivative and S from one derivative. So this is the Laplace transform of this equation. This can further be simplified to write in terms of IA as this. And then again, if you take Laplace transform of equation 2, so equation 2 was EB equal to KB times d by dt of theta. So if you take the Laplace transform of that equation, what you get is EB function of S will be equal to KB S theta S. We call this equation as 6. So if you take the Laplace transform of equation 3, so equation 3 is nothing but the equation that you obtained after applying KVL on the armature side, which was input voltage equal to all the other voltage drops. So if you apply KVL at this, if you take Laplace transform of that equation, you get VI is equal to RA plus SLA times IA plus EB. All variables are function of S now. If you substitute the values of IA, EB from 5 and 6 in 7. If you look at equation 5 and 6, from equation 5 you have IA given by this expression, from 6 you have EB given by this expression. If you substitute these two expressions into 7, so you replace IA and EB by 5 and 6, you get this expression. So this is the ratio input upon output. In order to obtain the transfer function, you reverse it, you take the inverse of it to get the final transfer function, which is given by KT divided by RA plus SLA into S square J plus SB and plus KB KT S. So there is a slight correction that I have written here with a small KB. So and here it's written capital KB. So it doesn't have any difference. So it should be capital KB here. Or all the terms should be small k's or capital K's. So there is no difference in this meaning. So it doesn't mean that this is in time domain and this is in Laplace domain. It doesn't have any difference, it's a constant. Now if we try to obtain the block diagram representation of the DC motor with armature control. So if you remember that in case of representation of a block diagram, you have input shown on the leftmost side and output on the rightmost side. So in this particular case, since VIS is the input voltage, the input to the system, while the displacement theta S is the output. So we are going to obtain the block diagram in such a manner that the input will be represented on the leftmost side while the output at the rightmost side. So this can be done by using the equations that we obtained previously. So if you look at equation 7, you see that VIS, which is input, is given by an expression of this form. So using this expression, you can obtain. You're going to feed VI, and since this is a voltage value, VI is a voltage value, EB is again a voltage value, while the multiplication of I with RA plus SLA is a voltage value. So from this expression, you can obtain the current IA by subtracting EB from VI. So if you subtract VI minus EB and divide this by this expression RA plus SLA, this will give you IA. So we can obtain the block in this form. So the block diagram representation of equation 7 is given here. So if you feed to the and subtraction or the addition will be always done using comparator. So if you look at this comparator, you're going to give VI with a positive sign and EB with a negative sign. And what you're going to do is you're going to get an output from this comparator as VI minus EB. And if you multiply this difference from the expression 1 over RA plus SLA. So this is RA plus SLA. If you take this to the denominator at the left side, so what you get is the current IA. So I guess this explains how to obtain block diagram from equation 7. Now, how do you obtain theta? Theta, which is the output. So if you look at equation 5, so you see that if you are going to, because we are going to use equation 5, since we obtain IA from this block representation, and if we are going to fit this IA to a block accompanying KT upon S square J plus SD, then that will give you theta S. Since theta S is equal to IA multiplied by KT divided by S square J plus SD. So this gives you the block representation of equation 5, where you feed IA as input to this particular block, and the gain of this block or the transfer function of this block is obtained from these expressions. So if you do this, you're going to get the output theta S, which is the final output of the system. And now if you're going to connect these blocks, the two blocks, this one, since IA obtained from this particular representation fed to this block will give you theta S. But you still have EB floating. So you don't know where EB is coming from. So in order to know where EB comes from, you will be using equation 6. So if you see equation 6, EB is given as KBS times theta S. So if you're going to multiply the output theta with a block SKB, so if you're going to feed theta into the block 1 upon SKB, sorry, there is a correction, it should not be 1 upon SKB, rather this should be SKB. So here's a slight correction. I've written here 1 upon SKB. It shouldn't be SKB. 1 upon SKB. It should be SKB in numerator. So theta multiplied by SKB will give you EBS. So now if you're going to connect all the three block diagrams, this one with this one and this with this one, so you will get the final block diagram representation of the system as follows. So VI to the comparator multiplied by this block gives you IA, further fed to KT divided by S square J plus SD gives you the output theta S. This theta S again taken as feedback multiplied by SKB. If you multiply theta by SKB, you get EB, which is fed back to the comparator. So this is the final block diagram representation of the armature controlled DC servo motors. So I guess this makes clear how armature controlled DC servo motors operate. So if you have any question, you can ask me. If you are not able to understand anything, then you can ask me question related to the same. I guess it's clear to all. Does anyone have any problem or question related to what I have taught to you today? So I had few questions to ask to you people. All right, my question to you is, where does back EMF come from? Can anyone answer where does back EMF come from? Why do you experience back EMF? Is it always there? Is it something because of presence of magnets? Is it because it exists only during operation of motor? Well, why I asked you these questions is that because I want to explain what is the importance of this block. Because if in the next topic I'll talk about the field controlled DC motor. So in that case, you will observe that there will be no feedback coming in the form of this particular block. So there you'll see that the block representation is an open loop representation. While in case of armature controlled DC motor, you have a closed loop representation of the system. So one important conclusion that you can draw from this closed loop representation is that since we saw that EB is nothing but it's equal to S KB times theta S, where S theta is omega. Omega is the angular speed, which means that EB, the back EMF is proportional to angular speed. So this is something that you already have been taught previously, since you know that the back EMF increases as the speed of the motor increases. So if you look at this particular block, if we assume that the motor is operating at a constant angular speed, in that case the output will be omega. So if you're going to take omega here, then you will be placing a block S over here. So if you place a block S here, let me write this for you. So if I suppose use this S and place it over here. So now what I get as output is omega. And let us assume that this motor is operating at a constant angular velocity of omega s. The omega is the output, which is then multiplied by the term kb to give eb. In case if you're going to load this motor, or you're going to change the value of load, let's say it was operating at a certain load L1 and you increase the value of load to L2. So the increase in load will cause the angular speed to drop, for momentarily drop. So for a small duration of time, you'll have the angular speed drop, and thus the speed of the motor will reduce and the back EMF will reduce, since EB is proportional to omega, or EB is equal to KB times omega. In case if the speed drops, the value of EB drops, this will reduce, and the difference VI by minus EB will reduce. So error will in that case increase. So as soon as error increases, IA will increase, the armature current increases, and that is why the armature controlled DC motor will draw more armature current from the source. So it will be drawing more current, and thus it will try to bring back the speed to its desired values. So as soon as speed comes back to its original value or the reference value or whatever you fix it as set point, then the error will reduce. It will go back to zero. So this is how the armature controlled DC motor will be operating automatically in closed loop fashion. So this armature controlled DC motor on changing load, if you're going to change the load, the value of armature current drawn by the motor will change. So if the load increases, the armature current increases. If the load decreases, the armature current reduces. So this is how load is proportional to armature current, while VI remains fixed. So it will be set by the user, while the armature current will always depend upon the variable load. So I guess this is clear to all. You can, if you like, revise the stuff that you have been taught in the previous year related to DC motors. Any question, anyone? Then the next class I'll be teaching you the field control DC servo motors. And now I am going to finish this meeting. If anyone has any question, you can ask me. All right, then thank you. You can, if you have any question, you can post me on my email ID, or you can post me on Google Classroom privately.